Hey guys, welcome to the 7th video of the Math 9A SI series. Today we're going to be looking at a little bit more continuity with the Intermediate Value Theorem, and then we're going to move on to infinite limits. Okay? So the Intermediate Value Theorem, or IVT, as I'll call it throughout these slides, says that let f be a continuous function on the closed interval AB, and without loss of generality, let f of A be less than f of B. Then for every value y, where f of A is less than y is less than f of B, there's at least one value c in the open interval AB, such that f of c is equal to y. So what is this saying? Basically, what we can pull from this is that if f of x is continuous over an interval AB, then we know that f of x will achieve every single y value that's between f of A and f of B. So why do we know this? So the first thing we want to recall is the definition of continuity. For the purposes of this, we want to think of a continuous function as a graph or a function that we can draw without ever lifting our pencil off the paper. So knowing this, the most simple continuous f of x we can draw is just going to be a straight line, right? Since that's the straightest path between f of A and f of B. And we notice that if we can pick any y that's between f of A and f of B, and for some c value, f of c is going to equal to y, no matter what. Because we never lift our pencil off the paper, we're drawing this line between the two. So that means we have to touch every y point between them at least once. So this is the most simple example of the proof, but let's look at a couple more real quick. So we can draw any kind of like funky graph between f of A and f of B. And we see that even if we're jumping up and down or flatlining and coming up at the last second, or even if we're exiting this boundary, we're going below f of A here and we're going above f of B here, no matter what, we're still going to be touching all the y values between them at least once. Like here you can see we're touching whatever this y value is more than once. We're crossing it twice. But something over here, we know we're at least hitting once. This is the whole idea behind this proof is basically just because of continuity. We can't pick up our pencil when we're drawing, so there's no way for us to jump from this y value up to here suddenly without also touching all these other points in between, right? And you can try this yourself too. Try like weird funky graphs and see if you can find a way to break this proof, but it's impossible. So applying IVT. So given this f of x, which is equal to x cubed plus 2x squared plus 3x minus 4, we're asked to use IVT to prove that there's a root in the interval 0, 2. And then we're also asked, can we use IVT to guarantee that for some c, f of c is equal to 21? Let's start by finding our endpoints. In this case, we have f of 0 and f of 2. So we just do this by plugging in 0, right? So we plug in 0 here, these all 0 out, and we're just left with minus 4, right? Here, f of 2, we have 2 cubed plus 2 times 2 squared plus 3 times 2 minus 4, which equals 8 plus 8 plus 6 minus 4, which simplifies to 18. So using IVT, we guarantee that f of x is going to achieve all y values between -4 and 18 over the closed interval 0, 2. Thus, f of x must have a root in this interval, since -4 is less than 0 is less than 18. So we know 0 is one of these y values in this boundary we've created. So we know our function f of x has to hit it at least once. It may be possible, this is for part 2, it may be possible that f of x does achieve 21 over the interval 0, 2, but we can't guarantee it by IVT, since 21 is outside of this boundary we've created from -4 to 18. So we can't rule it out altogether that we won't hit 21 ever between this boundary, but IVT only guarantees things before negative, or they only guarantee things between -4 and 18, right? For this problem, at least. So now, shifting gears to limits at infinity. So infinite limits refer to either of these things of this form. So you have a limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x equals L. And our horizontal asymptotes, much like vertical asymptotes, but in this case, we're checking our infinite limits to see if they equal L. And if they exist and they do equal L, we say that the line y equals L is a horizontal asymptote of f. So to find horizontal asymptotes, we just need to see if any infinite limits of f of x exist. So here's an example. We have f of x equals 1 over absolute value of x. Here we see that the limit as x approaches infinity of 1 over the absolute value of x is equal to 0. We see as we continue this way, we're going to get smaller and smaller, closer to 0, but we never touch it. But we do know we're approaching 0. And the same thing with negative infinity. We're coming this way, we're coming this way. Never hitting 0, but we get super duper close. So because of this, our f of x has a horizontal asymptote at y equals 0. Here's some limit laws. I think the biggest takeaway here is that the infinite limit of a polynomial like this, x to the r, where r is greater than 0, that's just going to be equal to infinity, right? And we can also see that the limit as infinity in the denominator, if we take the limit like here, we know that this x to the r is going to evaluate to infinity in our denominator. So if we have 1 over something that's approaching infinity, that's just going to be 0. So that kind of makes sense, right? If we have a super large number in the denominator, we're going to get a super small number coming out of it. So if you think of it like 1 over infinity, so an infinitely large number, we're going to get an infinitely small number, which is just going to be approximately 0, right? Here's some helpful identities. I'm not going to read it all out, I don't think, but if we have something where we have like a polynomial over another polynomial, then we can go ahead and check the highest power of the top and the highest power of the bottom and compare them. And we have these 3 cases. One where the highest powers are the same, one where the highest power on the top is less than the highest power on the bottom, and one where the highest power on the top is greater than the highest on the bottom. These can be useful to memorize, but in general, I think it's probably better for you if you can just derive it, especially since the third case actually does require us to derive it most of the time because we want to see whether we're hitting infinity or negative infinity. But it can be useful to look at a glance at a graph or a function and say, like right off the bat, what the infinite limit is going to be. So we have a couple examples. So let's go to the whiteboard and work on these. So here's our first example. We have the limit as x approaches infinity of e to the 1 over x. So this is kind of going back to our composition, right? So the first thing we want to do is apply the limit to the one part that it applies to, which is 1 over x. So let's find this first. So we have limit as x approaches infinity, 1 over x. This is something that's pretty easy to see. So we just have 1 on the top and our x is approaching infinity on the bottom. So this is just going to be equal to 0, right? This is just something that's good to know. This will be mostly what infinite limits are going to be. So now we see that we're just left with e to the 0. We can leave the limit as x approaches infinity out of here because now we don't have anything else in terms of x. So e to the 0, and you might recall that that's equal to 1. So the answer for the first one is just 1. So here we have our second example. We have the limit as x approaches negative infinity of 2x cubed minus 3x squared plus 4x plus 5 over 5x cubed minus 4x squared plus 3x plus 2. So the way we want to go about it is using the properties of limits of infinite limits that we saw earlier. And we want to use the fact that if we have 1 over some polynomial, we know that as x approaches infinity of that, it's just going to approach 0, right? But we don't have anything of that form, right? But we can get it in that form by dividing both the top and bottom by the highest power of both. So in this case, they're the same. So we can just go ahead and multiply both by 1 over x cubed. So the top and the bottom. So if we evaluate this, we're going to get, let's rewrite the limit. We're going to get that this is equal to 2, since x cubed is going to cancel out, minus 3 times 1 over x plus 4 times 1 over x squared plus 5 times 1 over x cubed. Apply the same thing to the bottom. 5 minus 4 times 1 over x plus 3 times 1 over x squared plus 2 times 1 over x cubed. So we see that if our limit as x approaches infinity, that each of these with the polynomial in the denominator, each of these are just going to come out to be 0. So we're basically left with just the parts at the front, which is going to be 2 over 5. So that gives us that our limit is 2 over 5. And I kind of left that out, but you see that this is negative infinity here, but it doesn't really matter in this case because these are all just going to be evaluated to 0 anyway, so the sign doesn't really matter as much here. We just know that 2 over 5 is the part that matters. Okay, so in this case, it could be infinity or negative infinity, and we're going to get the same result. Here we have our last example, which is limit as x approaches infinity of 4x squared plus x to the 6th over 1 minus 5x cubed. So in this example, we're going to do something a little bit different from the last one, and I think it'll make it more clear why the answer is what it is. So here, we're going to pull out x cubed from the top and bottom. And if we do that and rewrite it, we get x cubed times, so pulling it out here, we're going to be left with 4 over x, right? If we distribute that back out, we're going to get 4x squared, okay? And pulling it out here leaves us with x cubed over here. Since x cubed times x cubed is just going to give us x to the 6th. Same thing down here, pulling out x cubed, we're going to be left with 1 over x cubed here and minus 5 here. Okay, so now we can actually cancel these x cubes, right? So we don't have to worry about them anymore. And we're just going to be left with limit as x approaches infinity of 4 over x plus x cubed over 1 over x cubed plus 5. Oh, my bad. That's not plus. We're going to be left with just minus 5. So here we see that this portion, is going to go to 0 since we have x in the denominator. This part's going to infinity. This part's going to 0. And this part is just minus 5. So we're actually going to be left with infinity over minus 5. Well, what's that going to be? We have a negative involved here, and we're dividing. So this is actually going to be equivalent to negative infinity. So interestingly here, when we plug in infinity, we're actually getting that our infinite limit is going to be equal to negative infinity. And we notice that that's because of the sign that's in front of our highest term here at the bottom. We have negative 5x cubed. So you want to pay attention to all the signs when we're dealing with this case in particular, where the top part has a higher power than the bottom. This is the weird case, okay? And that's it. Thank you guys so much for watching this video. Please let me know if you have any questions, either by commenting below, emailing me, coming to office hours, anything. I'm always happy to help you guys out. If you have any comments or criticisms, anything I can improve upon, please let me know that as well. I want to keep improving with every video I put out for you guys. I want to be as helpful as possible. Yeah, so that's it. Thank you guys. See you.